Then we can get started on discrete math. Welcome back, everybody. Welcome to discrete math. That's our small talk for the day. More small talk after class. But right now, we have to talk about section 4.1, which is what we started last time and what I've been hyping up for like weeks and weeks and weeks and weeks and weeks and weeks and weeks now. And the reason is section 4.1 is where we actually start proving things. So if we go over it, if we go over it, really everything we've done so far has just kind of been us building a foundation for us to talk about how to prove actual mathematical things. I mean, so far, let's talk about what we've had. We've had statements, right? And those kind of came from just, we kind of assumed things can be true or false, right? So when we talk about statements, statements are only things that we assume to be true or false. And we kind of make this assumption that everything is either true or it's false. It seems like a really basic assumption, but it's an assumption. Some people don't make that assumption. There's whole branches of math of people spending their entire careers doing things where they don't make that assumption because we've ran out of ideas in math, apparently. But yeah, so that was an assumption, right? And then we had our logical operations, right? Like and, or, not, XOR, implies, biconditional, all of those 16 possible ones, right? And all of those are just defined. Right, we just defined like what those what those were with truth tables, right? And those just came from statements. So we have made our assumption of statements existing, and then from that we naturally had logical operations. And then we had our logical laws. And those were just proven from operations. So like logical laws, it's really nothing to new. We just prove those work based on the definition of those operations. The definitions of operations or based on truth tables coming from statements, right? And after logical laws, we had predicates, which were once again defined from statements. We just define it to be that thing where if you plug something in, it becomes a statement. And then the last thing we did was quantifiers. For all there exists, that kind of thing. And all of those, and these were another kind of assume to work the way we think is what I'm writing. The way we think. If you remember that random lecture on for all and there exist statements, or for all there exist statements being kind of related, the yin-yang property with like and or. For finite cases, we could define them as and or. For infinite cases, we had to assume they work the way we think, meaning that for all just means everything in the set, even if it's infinite. And there exists just means one thing in the set, even if it's finite. And then they're the opposites of each other, even in the infinite case. The point is, oh, and I forgot arguments. I should go in here somewhere. And these are proven from truth tables. Proven from definition of operations. So really, this whole time, everything we've been doing has been building up all of these different things, which really kind of all come from the assumption that things are true or false, and the assumption that for all and there exists to work the way we think it does. That's it. We've made two or three, depending on your count, very basic assumptions, and we've been able to build all of this logical speak, right? And now that we have this logical speak built, we can actually start to prove really cool, interesting things. So, any questions on this? This is like our meta-analysis of logic right now. This is just me kind of recapping what we've done so far. So that you guys know that, I mean, we are really building this from scratch. This is what we have. So,